Some of the most productive ecosystems on Earth are found along shorelines. Salt marshes are coastal wetlands dominated by salt-tolerant plants that are intermittently exposed to air and then completely submerged as tides ebb and flow. They are the most productive source of food energy per acre of all known ecosystems.
Salt marshes are important because they provide energy source. They provide carbon, and when it breaks down, it leaves and goes into the estuary, which starts the food chain. They're great for storm erosion. They protect the shore inland. They have a habitat for fish.
Seagrass meadows consist of narrow-leaved flowering plants that grow in vast underwater meadows on the seafloor. 1 acre of seagrass meadow can support 40,000 fish and 50 million invertebrates, which are vitally important to marine fisheries. Seagrasses and salt marshes buffer coasts from storm and tidal surges, trap sediments to ease coastal erosion, absorb rainwater, filter runoff, and improve water clarity and quality. Unfortunately, several phenomena destroy or pollute these important ecosystems. The biggest threat to salt marshes is coastal development. Construction of dikes, levees, and roads often alter tidal hydrology by restricting water flow to and from a salt marsh. This, in turn, reduces salinity and lowers the water table, creating favorable conditions for invasive species such as Phragmites, the common reed. One effective restoration strategy is removal or modification of problematic structures to reinstate tidal flooding. In Chevery Creek, Nova Scotia, local NGOs partnered with schools and community leaders to address an ineffective road culvert that was restricting tidal inundation. After garnering support from stakeholders and modeling hydrologic data, an aluminum arch culvert was constructed, increasing the opening size 7-fold and restoring tidal flow.
It doesn't do any good to put something in if it's going to be continually polluted, say from runoff. So let's say they have a lot of beach houses and they fertilize all their lawns, and they put a wetland in front of it thinking it's going to be great, and it turns into not salt marsh anymore, but say Phragmites, which is a horrible invasive species, because they just keep pouring nutrients in.
Physical removal of invasive vegetation can accelerate restoration, but can also be costly, often requiring excavation in order to ensure that roots and rhizomes are completely removed. Until just a few decades ago, salt marshes were considered wastelands, often intentionally filled for land reclamation. Restoration usually requires removing fill and recontouring the bank.
The early restoration that was done, some of it was a failure because people didn't understand that you had to get the elevation correct. The soils had to have enough organic matter, and you could not put salt marshes in places where the soils were too acid, there was not enough nitrogen.
Erosion also contributes to the loss of salt marshes. This can be combated by adding or reinforcing soil. On Barren Island in Maryland's Chesapeake Bay, a team of restorationists coordinated with the Army Corps of Engineers to use material from a nearby dredging project for bank stabilization. Large geotextile tubes were filled with sediment and placed just off the island. More sediment was then pumped in behind them. Finally, volunteers planted cordgrass plugs which fortify the sediment beneath as their roots grow. Salt marsh restoration is increasingly being used as part of a living shoreline strategy for coastal properties. Since salt marshes are alive, they can grow and adapt, making them more effective at stabilizing shorelines than hard structures such as bulkheads or concrete seawalls, which will eventually be undercut. Seagrass communities also face several threats. Wave energy and nutrient flow interruption due to increasingly intense storms damage seagrass communities. While seagrass species are adapted to handle natural disturbances, anthropogenic threats frequently exceed their capacity for recovery. Sewage and stormwater runoff reduce available sunlight. Dredging and boat propellers can cause mechanical damage and elevated turbidity levels, inhibiting photosynthesis. Soil erosion inhibits the ability of seedlings to take root. An innovative strategy uses oyster reefs as living breakwaters to reduce wave energy, creating conditions more hospitable to seagrasses.
With the seagrass beds, they've had to put in some other features, even to the point where they put in oyster reefs in front of the seagrass bed so that the waves don't basically tear them up so easily.
Once threats have been resolved, seagrass restoration often employs transplantation, which may use either plug methods or staple methods. In the plug technique, a hollow tube is placed over a mature seagrass specimen and pushed into the surrounding soil. The tube is then used to remove the plant and surrounding sediment and to transport it to another location. In the staple method, a seagrass specimen is removed from its soil with a shovel, and any attached sediment is shaken off. The specimen is attached to a staple and then placed into the soil. The staple anchors the plant until the plant's root processes allow it to adhere on its own. Distributing seeds may also be sufficient to restore a site. The effectiveness of seeding depends on the soil integrity and species involved. Some species, such as eelgrass, are particularly well suited to this method. However, water currents and erosion affect seeds' abilities to plant the soil. Natural recolonization is economically appealing, but is hampered by the same factors as seeding. Restoration may involve improving substrate by providing biodegradable surfaces to which seeds can adhere. Once the materials break down, the established seagrass can stabilize the soil enough for future seeds to take root. A 2005 project in Adelaide, Australia, pioneered the large-scale use of this method. Several biodegradable materials, including coarsely woven Hessian bags, successfully recruited seagrass seedlings. Restoring shorelines comes with challenges, as communities must make development decisions with the cost of actions and inactions in mind. As with other fields of restoration, funding is low, and there are numerous obstacles from a policy perspective.
It's very expensive. Right now in the state, if for an acre of wetland, to restore an acre, they estimate it costs somewhere between $230,000 and $250,000 an acre.
But the benefits of restoring shorelines are unmistakable. More productive habitats, carbon sequestration, and storm surge protection, among others. Coastal communities must prioritize restoring shorelines in light of their environmental and economic significance.
As I always say, restoration is not rocket science. It's actually far more difficult.